An important component of virtual reality is the ability for users to freely explore their virtual environment. However, locomotion in virtual reality is non-trivial because of a fundamental problem. Due to the different layouts of the physical and virtual environments, it's possible that an unobstructed path in the virtual world corresponds to an obstructed path in the physical world. Over the years, researchers have developed many different solutions to this problem, including teleportation, walking in place, treadmills, joystick controls, motion metaphors, path drawing interfaces, and many more interfaces. One potential solution to VR locomotion is redirected walking, which allows the user to travel using natural locomotion. Redirection works by slowly rotating the virtual world around the camera, which causes the user to subconsciously adjust their physical trajectory to counteract the virtual rotations and stay walking on their intended path in VR. So, for any given virtual path, a common question is to determine the optimal direction to steer the user to minimize collisions with unseen physical objects. In this example, we would prefer to steer the user to the left, since it avoids the obstacle on the right side of the physical space. However, that example is an oversimplification. For any given virtual path, there are an infinite number of physical paths we can steer the user on, which is determined by the speed of the virtual world rotations. Thus, there are two main questions in redirected walking research. How much can we steer the user around for a given path, and which is the optimal direction to steer the user? In this work, we focus on the first question. A lot of great work on redirected walking has been done over the years. While I don't have time to cover all of these works, there are a few takeaways we can learn from them. First, we know that redirection thresholds are volatile. A user's sensitivity to redirection depends on field of view, time spent in VR, user gender, walking speed, environment complexity, and more. This brings us to our first research question. Motivated by the advent of high dynamic range VR displays, we studied whether display luminance has an effect on redirection thresholds. Second, measuring redirection sensitivity is an expensive process because psychophysics takes a long time, measured thresholds can be inconsistent, and it interrupts the user's experience. Motivated by this problem, our second research question was whether there are any correlations between physiological signals and redirection strength, which might open the door for new methods of estimating sensitivity to redirection. To answer these questions, we ran a psychophysical experiment. We used the method of constant stimuli with rotation gains in the range of 0.6 to 1.4, with 12 trials per gain in each block. We had 2 blocks, one with photopic display brightness and one with mesopic display brightness. The data we collected were users' perception of the applied gain, their gaze data, and the HMD pose data. We had 11 participants total, with 4 female. For luminance, we found that there was no significant effect of display luminance on users' sensitivity to redirection gains. For gaze data, here is a sample of a user's gaze trace for one trial. On the left is their left eye gaze position. On the right is a plot of their gaze amplitude with saccades highlighted in green. We fit a multilevel model to users' gaze data and found the following. There was a significant positive effect of redirection strength on users' average gaze velocity and saccade frequency. There was a significant positive correlation between trial duration and blink and saccade frequency, and a negative correlation between trial duration and gaze velocity. Finally, we found a significant correlation between time spent in VR and average gaze velocity. For HMD pose, we measured the average spread of users' HMD position as a proxy measure of postural stability. We found a significant positive correlation between redirection strength and postural sway, meaning users' posture was more unstable as the redirection strength increased. To recap, we had two main research questions. First, we studied the effects of display luminance on redirection thresholds. We found no significant effect of luminance. We believe that this is a sign that researchers should start to consider multisensory integration processes for self-motion perception in redirected walking. This is supported by the fact that multiple participants mentioned using different strategies for the photopic and mesopic luminance conditions. Second, we studied the existence of correlations between redirection and physiological signals. We found that gaze and posture data were significantly correlated with redirection strength and time spent being redirected. For future work, we believe that researchers should study correlations with different physiological signals like heart rate and skin conductance, and should study correlations during active walking tasks. Also, future work should try to disentangle the effects of simulator sickness and redirection. Finally, future work should incorporate the findings of physiological signals into redirected walking steering algorithms.